In this video, I will introduce the concept of magnetization, and before that, we will discuss the effect of magnetic field on materials. So in the previous chapter, we introduced the magnetic dipole moment, and we mentioned that atoms have electrons that have an orbital magnetic moment, which in the book notation is labeled as m sub L. And in fact, electrons also have another magnetic moment, which we call the spin. The spin magnetic moment in the book notation is labeled as m sub S. Now, these notations are a bit confusing because there are also quantum numbers that are labeled as m sub L and m sub S. So you should know that there are other notations for the orbital and spin magnetic moments, for example, mu sub L or mu sub S. Now, because this class is mostly at the classical physics level, not at the quantum level, then we should not have issues with the notations of the book. So I will keep the notations of the book unless the formula is quantum. So the classical picture you can have in your head for the orbital magnetic moment is that one. You have an electron orbiting around the nucleus. This moving mass has an orbital momentum L, and this moving charge can be viewed as an electrical current I, which creates a magnetic moment m sub L or mu sub L. Now, in quantum mechanics, the orbital moment L is quantized, and so is the orbital magnetic dipole moment. It is equal to minus the square root of L plus 1 times mu b. And mu b is a constant equal to E h bar over 2 times the mass of an electron. Its value is 9.27 times 10 to the power minus 24 ampere meter squared, or joule per Tesla. Now, for the spin magnetic moment, the classical picture that you can have in your head is that of the electron spinning around itself. That moving charge creates a magnetic dipole moment, m sub S or mu sub S. In quantum mechanics, this is also quantized, and it is equal to minus g square root of s plus 1 times mu b. And g is the gyromagnetic ratio, which is almost equal to 2 for an electron. Now, in a material, you have plenty of atoms, so you have plenty of magnetic dipole moments, and in general, they are randomly oriented. So this is if the applied magnetic field is 0 or if it is negligible. But if we apply a magnetic field, then all the small magnetic dipole moments will align in the directions of the magnetic field. And we call these materials paramagnets. For example, palladium, vanadium, lithium, oxygen are paramagnetic. There are materials for which the magnetic dipole moments can be induced by a magnetic field, and the induced magnetic moment aligns in the opposite direction as the applied magnetic field, and we call these materials diamagnets. For example, graphite, boron, bismuth, copper, zinc, gold, water are diamagnetic. And there are also materials for which the magnetic dipole moments will spontaneously align together in the same direction. Okay, even if there is no applied magnetic field, all the magnetic dipole moments will pick a direction and all align in that direction. The direction of alignment can be random, but a lot of magnetic dipole moments will pick the same. And if you apply a magnetic field, then you can favor a specific direction, which will be the direction of the applied magnetic field. And we call these materials ferromagnets. Now, for example, there is iron, cobalt, nickel, which are ferromagnetic materials. Now, here are more examples of ferromagnetic materials, and for each of them, the second column indicates the Curie temperature in Kelvin. The Curie temperature is the temperature below which the atomic dipole moments align spontaneously. So these materials are ferromagnetic below the Curie temperature. So here is a question for you. If these materials are ferromagnetic below the Curie temperature, then what are they above the Curie temperature? Okay, if you guessed paramagnetic, you're correct. Above the Curie temperature, the thermal energy is large enough so that the atomic magnetic dipole moments will be randomly oriented. And this is what we call paramagnetism. We will come back to ferromagnets later in this chapter, and we will discuss their applications in our everyday lives, in our technologies. But before that, we need to review the effect of torques and forces on magnetic dipole moments. So first, let's consider a rectangular loop with an electrical current. This loop has a magnetic dipole moment that is pointing out of the screen. And let's suppose that there is a uniform applied magnetic field that is also pointing out of the screen. So this is the first case we consider, the case of a uniform field parallel to the magnetic dipole M. Because we have a wire with an electric current inside a magnetic field, B, then we are going to have a Lorentz force on this wire. Right? And as we learned last lecture, the Lorentz force is F equal the integral of I cross B dl, where we integrate over the length of the wire. So here is a question again. What is the direction of the force on the left side of the loop? Okay, if you answered that the force is pointing left, then you're correct, right? You know how to find the directions of the cross product using the right-hand rule. Okay, then if you look at the force on the right side of the loop, it is pointing to the right. And if you consider the force on the top part of the loop, it is pointing up. And if you consider the force on the bottom part, it is pointing down. So the sum of all these little forces, when you do the integral over the entire loop, is equal to 0. The net force is 0 if the magnetic field B is uniform, or equivalently if the loop is so small that we can consider B uniform over the size of the loop. Now we will consider the case when the magnetic field is still uniform, but the loop is tilted. Suppose the field is along the z-axis, but the loop is tilted so that the magnetic dipole moment M makes an angle theta with the direction of the field B. Suppose also that the loop is a rectangle with side lengths A and B. The side view is like this. We have the magnetic field along Z, the loop is tilted so that its magnetic dipole moment makes an angle theta with the Z-axis. Okay, do again the cross product to find the direction of the Lorentz force on each section of the loop. The side is going to feel a force that is like this, pointing towards plus x. The opposite side will feel a force in the opposite direction. The top side will feel a force pointing left, and the bottom side will feel a force pointing right. Again, the net force will be 0, but this time there will be a net torque. This torque is very clear on the side view here. The force on the top is pointing left, and the force on the bottom is pointing right, and this will result in a net torque that will tend to rotate the loop around the x-axis. So let's calculate the torque about the origin. The torque is R cross F, and the angle between R and F is theta. So adding both forces, we can get A times F times sine theta along x hat. Now, the length of the wire that contributes to the force is small b, so the Lorentz force is I b small b. So the torque is equal to A times I times B times small b times sine theta along x hat. But IAB is equal to the magnetic dipole moment of the loop small m. So we can write that the torque is equal to mb sine theta along x hat. But since the angle between m and b is theta, then you recognize a cross product. Right? The torque is equal to m cross b. And this is a result to remember. The torque about the origin that the magnetic field exerts on the magnetic dipole moment is m cross b. This relation is valid for B uniform or for an infinitesimal loop, because if the loop is very small, then you can always consider B to be uniform over the size of the loop. And you can see that the effect of this torque is that it tends to align the magnetic dipole moment with the direction of the magnetic field. This is the effect that we call paramagnetism. When you apply a magnetic field, the atomic dipoles will align in the direction of the magnetic field. Now, there is an analogy with the electric dipole moment. We had seen that the torque about the origin on an electrical dipole moment is equal to P cross E. We also showed that if the dipole moment is independent of the electric field and E is not uniform, there can be a net force given by P dot gradient of E. And we had also seen that the potential energy of the dipole is given by minus P dot E. So by analogy, we will skip the derivation here, and we will admit that the force on the magnetic dipole moment is given by m dot gradient of B. And that works if the magnetic dipole moment is independent of the magnetic field B. Now remember that this m dot gradient notation represents the variation of B in the direction of m. So if B is not uniform in the direction of the dipole moment, then there will be a net force. And also by analogy, the potential energy is given by minus m dot B. Again, you see that the potential energy is minimum when m and B are aligned in the same direction. So here's a question for you. Consider a horizontal current loop in the regions of non-uniform field at the top of a solenoid. And the current in the loop and in the solenoid are in the same direction. What is the force on the current loop? Okay, if you answered that the force is pointing down, you're correct. We can find these answers two ways. The first one is to find the direction of the force from the Lorentz force, which is given as the integral of I cross B dl integrating over the wire. If you look at the direction of B, it is pointing up and tilted outward. So if you do your cross product, you find that the force is pointing down and also outward. Because of the symmetry of this situation, the radial component of the force will cancel out when you do the integral over the whole loop. And so in the end, we obtain a force that is pointing down. Now the second method is to use the force on a magnetic dipole, m dot gradient of B. Remember that this is the variation of B in the direction of m. For the loop, the magnetic dipole moment is pointing up. And so what is the variation of the magnetic field in the up direction? Well, the field is decreasing as you go up. As you go up away from the solenoid, the field is decreasing. And so because the field is decreasing, its variation is negative, so the force is pointing down. Now here is another question. A square loop is located at a distance r from a circular current loop. And the square loop is free to rotate. What will be its equilibrium orientation? Okay, if you answered that it will be pointing down, you're correct. Again, remember that the circular loop is going to create a magnetic field which is pointing downward at the location of the square loop. Right, you have the magnetic field loops like this. And so because the square loop also has a magnetic moment, the magnetic field will create a torque on the square loop, which will tend to align the magnetic dipole moment with the direction of the field B. So B is pointing down, the square loop will rotate to have its moment pointing down. You can also get these results from the potential energy. Minus m dot B, the square loop will rotate and minimize its potential energy. the minimum potential energy is obtained when the dipole moment is aligned with the magnetic field. Now we will discuss the effect of magnetic field on atomic orbits. Consider the orbit of an electron that is rotating around a proton. First, we assume that there is no magnetic field. If you apply Newton's law, the only force on the electron is the Coulomb force of attraction from the nucleus, right? So Newton's law gives you the mass of the electron times the centripetal acceleration, v squared over r, equal the Coulomb force between the electron and the proton, so 1 over 4 pi epsilon 0, E squared over r squared. Now, let's say that we turn on a magnetic field. The magnetic field is uniform and is pointing up perpendicular to the plane of the orbit. With a magnetic field, we have now an additional force on the electron, which is the Lorentz force, right? QV cross B. And we will assume that the speed of the electron will change so that the radius of the orbit remains the same. And we will write the new speed v bar. So Newton's law becomes me times v bar squared over r is equal to the Coulomb force 1 over 4 pi epsilon naught E squared over r squared plus the Lorentz force E v bar times b. Now we combine these two equations. So let's subtract the first one from the second one so that the Coulomb force will cancel. And then we have E v bar b equal me over r times v bar squared minus v squared, which we can rewrite as me over r v bar plus v times v bar minus v. And now it's reasonable to assume that v and v bar are almost equal to each other. Right? The delta v, which is v bar minus v, is very small. So E v bar b is similar to E v b. Then we have me over r. Then v bar plus v is similar to 2v. And v bar minus v is delta v. Then the v cancels out. And we obtain delta v equal EBR over 2me, which is larger than 0. So in summary, when we turn on the B field, then delta V is positive, means that the electron speeds up. But really, is that possible? How can the electron accelerate if the magnetic field does not do work? In fact, you will see in the next class, we will see that a change of magnetic field, a change of B field induces an electric field, and then the electric field can do work on the charged electron. So in fact, there is no contradiction. B does not do work, but the change of B does work. Okay, so we saw that turning on a B field will change the speed of the electron by delta V, which is equal to EBR over 2me. But this change of speed means that the dipole moment of the electron orbit will change. We know that the magnetic dipole moment is equal to the current I times the area of the orbit pi r squared. The current is charge per unit time, so it is minus E per period t, where t is the period of the electron on its orbit. So the electron does a full turn, which is 2 pi r at the speed v. So t is 2 pi r over v. Now let's combine these equations. We have the magnetic dipole moment m equal minus 1/2 EVR along z hat. So when the speed of the electron changes by delta v, then the magnetic dipole moment will change by minus 1/2 E delta v r along z hat. Okay, since delta v is equal to EBR over 2me, then we can write delta m as minus 1/2 E, then EBR over 2me times r along z hat. And so that is delta m is minus E squared r squared over 4me times b along z hat. And since B is actually along z hat, then we can write this as minus E squared R squared over 4me times vector B. Now you see that the change of magnetic dipole moment M is opposite to the B direction. Now we won't do it here, but if we had chosen the magnetic field pointing down in the same direction as the dipole moment, then the electron would slow down. That is still changing the dipole moment in the minus B direction, still changing in the direction opposite to the direction of the magnetic field. And so in summary, when B equals 0 in an ordinary material, the dipole moments are all randomly oriented. And when B is different from 0, each atom will pick up a little extra moment, and all the little extra moment will be anti-parallel to B. That is what we call diamagnetism. Now, a measure of the paramagnetic or diamagnetic effect is the quantity called the magnetic susceptibility. And we will introduce susceptibility in the next video, but for now I will just discuss the value of magnetic susceptibility for a few materials. Now, one of the materials with the largest diamagnetic effect is pyrolytic graphite. Its magnetic susceptibility in SI units is minus 40.9 times 10 to the power minus 5. And so it is negative for a diamagnet because the dipole moment align opposite to the magnetic field. The magnetic susceptibility measures how the material is susceptible to an applied magnetic field. So it measures what is its relative response to an applied magnetic field. So if the response is to align the moment to the opposite direction of the magnetic field, then the susceptibility is negative. So for pyrolytic graphite, this value is so large that the magnetic force on the induced dipole can be large enough to overcome gravity. And so when you put a piece of graphite on a strong magnet, it can levitate. Another material with a large diamagnetic susceptibility is bismuth. And even water has a relatively large diamagnetic susceptibility. So objects that are made of water will essentially repel a magnetic field. And if this magnetic field is strong enough, then they can levitate. For example, Andrew Geim was able to levitate a frog in a magnetic field of 16 Tesla. Andrew Geim is a Dutch-British physicist. He and Michael Berry got the Ig Nobel in 2000 for this experiment. Now, the Ig Nobel is sometimes considered a joke. So when Andrew Geim was contacted to receive the Ig Nobel, he was not sure he should accept it. So he asked his colleague Michael Berry, who had written the theoretical explanation for the levitation. He asked him, should I accept this Ig Nobel Prize? And Michael Berry told him, yes, you should accept it. And so Andrew Geim replied, okay, I will accept the prize if you also give it to Michael Berry, who wrote the explanation for the frog levitation. And so in the end, they both got the Ig Nobel. Now, the Ig Nobel is not as prestigious as the Nobel Prize, but Andrew Geim actually does not care because in 2010, he also got the Nobel Prize in Physics for his work on graphene. Now, Andrew Geim is a very funny guy. He also has he also published a paper with one of the best co-authors, the hamster Tisha. In 2001, you see he published this scientific article on the detection of Earth's rotation with a diamagnetically levitating gyroscope. Andrew Geim was the first author of that paper, and the second author was HAMS Tisha, the hamster Tisha. And here is the video of the levitating frog.
Can you look at me? Because I like to show this is the magnet which is beyond. If you have a look here, this is.
Now, do you know what happens when you put a frog in a large magnetic field? It levitates, yeah, but then what happens?
Don't touch anything, please.
It changes into a grasshopper. And then what happens to the grasshopper? It changes into flowers.
There is no problem with putting a man, to force a man by this magnetic levitation to fly in the air. So technically we can do it with you without any problems. We put it here, let's put it here. As you see, it's alive and moving quite happily. No tricks.
No tricks, huh? Okay, now let's watch these cool scenes from Magneto, who can control metals. Okay, you see, Magneto's power are very strong, but really, I think they are overrated. Okay, because Magneto only controls metals, but if he would control magnetic field, then he would control all atoms, right? All objects, even living animals. He would be able to levitate a frog, a human body. He would truly control everything. Okay, before we conclude, let me add one more concept. It's a quantity called magnetization. We use the letter M, uppercase M, for magnetization, and it represents the magnetic dipole moment per unit volume. So we have all the atoms, and each atom can have a magnetic dipole moment, and the value per unit volume is the magnetization. It is a quantity that has the units of ampere per meter. So let's summarize what we learned. We saw that when you apply a magnetic field and you have dipole moments, the effect of the magnetic field is to create a torque on these moments. And if the field is non-uniform, there can be a net force on the moment. And we saw that the moment in a magnetic field will have a potential energy. The result of the torque is that it tends to align the moment in the same direction as the magnetic field. And this is what we call paramagnetism. But another effect of the magnetic field is that it adds up an extra moment, and all the extra moments are anti-parallel to B. This is what we call diamagnetism. So in some materials, there is no magnetic dipole moment, so only the diamagnetic effect exists. But if there is a dipole moment, usually it wins and the paramagnetic behavior is observed. And finally, we defined a new quantity, the magnetization, which is the dipole moment per unit volume.